Have you ever looked up at your roof and wondered, is this really the best we can do? For years, silicon solar panels have been presented as the undisputed champions of the clean energy revolution. We install these heavy, rigid glass panels on our rooftops, hoping to lower our monthly electricity bills and move a little closer to that dream of energy independence. There is something deeply satisfying about watching your home operate on nothing more than sunlight falling from the sky. But what if the technology we have spent the last 70 years improving is finally approaching a wall, a physical ceiling it simply cannot break through? And what if scientists, thousands of miles away, have developed a crystal that is inexpensive to manufacture, absorbs light around 10 times more strongly than silicon, can be processed almost like printing ink, and is now pushing solar efficiency records to levels that once seemed impossible? Today, we may be standing at the beginning of one of the biggest transformations in clean energy in decades. And this breakthrough could affect far more than giant utility-scale power plants. It could eventually change how we save money, heat our homes, generate electricity, and optimize the places where we live. Welcome back to The Roots Survived. Today, we are going behind the scenes of a quiet but incredibly competitive global race centered around a remarkable material called perovskite. China is scaling this technology at an extraordinary pace, pushing it from laboratory experiments toward real-world manufacturing, while setting records that are forcing the rest of the solar industry to pay attention. But does this really mean the silicon era is coming to an end? Can a crystal processed almost like liquid ink eventually replace the solar panels we know today? Or is perovskite still a fragile, unstable, potentially toxic technology that could fail long before homeowners ever recover their investment? Let's dig into what is really happening. Part 1. The silicon ceiling. Why your current panels are maxing out. To understand why researchers are searching for something new, we first need to understand the limits of what we already have. If your home has solar panels today, there is a very good chance they are made from crystalline silicon. And silicon deserves enormous credit. It is reliable, durable, and has powered the growth of the solar industry for decades. But there is a hidden cost behind this remarkable material. Producing a silicon solar panel begins with raw quartz that must be processed, melted, and transformed into an extremely pure silicon crystal. The process requires enormous furnaces operating at temperatures around 1,500 degrees Celsius, or nearly 3,000 degrees Fahrenheit. Think about how much energy must be consumed simply to manufacture a technology designed to generate clean energy. A traditional silicon panel can require years of operation before it produces enough electricity to compensate for the energy used during its manufacturing process. But manufacturing energy is not even silicon's greatest limitation. The bigger challenge comes from a physical principle known as the Shockley-Queisser limit. Every photovoltaic material has something called a band gap. You can think of it as a filter that determines which portions of sunlight the material can effectively convert into electricity. Silicon has a band gap of approximately 1.12 electron volts. Because of this, part of the energy contained in high-energy blue and ultraviolet light is ultimately lost as heat. At the opposite end of the spectrum, lower-energy infrared photons can pass through without producing useful electricity. That creates a fundamental efficiency ceiling. For a conventional single-junction silicon solar cell, the theoretical maximum sits at roughly 29.4%, and the residential panels available to most homeowners remain well below that theoretical limit, typically converting around 20% to 22% of incoming sunlight into electricity while producing roughly 400 to 500 watts per panel. In other words, engineers are already squeezing extremely hard to extract additional performance from silicon. Billions of dollars and roughly 70 years of development have pushed the technology remarkably far, but the remaining room for improvement is becoming increasingly narrow. If we want roofs that generate dramatically more electricity without requiring dramatically more space, we need something capable of moving beyond that ceiling. And that is where the story takes a very different turn. Part 2. The Magic Crystal. What is perovskite? Enter perovskite. When scientists use the word perovskite, they are not necessarily describing one specific material dug out of the ground. Instead, they are describing a particular type of crystal structure, commonly represented by the atomic arrangement ABX3. In photovoltaic research, scientists frequently work with hybrid organic-inorganic perovskites. In these materials, organic components, such as methylammonium or formamidinium, help provide structural flexibility, while an inorganic lead halide framework delivers the electronic properties needed for solar energy conversion. You can imagine it as an organic cage surrounding a framework containing lead and halide elements such as iodine or bromine. This unusual architecture gives perovskite two characteristics that make it extremely attractive for solar power. The first is its extraordinary ability to absorb light. Perovskite can absorb sunlight roughly 10 times more strongly than silicon. And that changes everything about how much material is required. An active perovskite layer, only a few hundred nanometers thick, thinner than something as delicate as a soap bubble, can absorb an enormous amount of incoming sunlight despite being dramatically thinner than a conventional silicon wafer. Because the active layer can be so thin, far less raw material is needed. That opens the door to solar devices that are lightweight, flexible, and potentially even semi-transparent. But the second advantage may be even more important when we start thinking about manufacturing cost. Perovskite can be remarkably easy to process. Silicon requires high-temperature furnaces and carefully controlled crystal growth processes. Perovskite, by contrast, can be prepared in liquid solutions that behave almost like ink. That means the material can potentially be deposited onto flexible plastic or glass using large-scale coating and roll-to-roll manufacturing methods similar in principle to industrial printing. Instead of relying entirely on extremely high-temperature furnaces and expensive wafer production infrastructure, manufacturers could eventually coat photovoltaic material across large surfaces using much simpler processes. And the speed at which perovskite technology has improved has been extraordinary. In 2009, early laboratory cells demonstrated efficiencies below 4%. By early 2026, certified single-junction perovskite cells had reached approximately 27.3% efficiency. In less than 2 decades, the technology had moved into the same efficiency territory that silicon required generations of engineering to reach. It has been one of the fastest technological climbs in modern photovoltaic research. But once researchers realized what perovskite could do, another question naturally followed. Why use it alone when you can combine it with silicon? Part 3. The Tandem powerhouse. 1 + 1 is way greater than 2. This brings us to one of the most exciting ideas in modern solar engineering, the tandem solar cell. Silicon and perovskite do not absorb sunlight in exactly the same way. Silicon performs well with portions of the red and infrared spectrum, while perovskite can be engineered to capture higher energy blue and ultraviolet light extremely effectively. So instead of forcing one material to handle the entire solar spectrum, researchers stack them together. A wide bandgap perovskite layer is placed above a conventional silicon cell. Sunlight reaches the perovskite first. The upper layer captures higher energy photons, while lower energy light passes through and reaches the silicon underneath. Each material handles the portion of sunlight it is better suited to convert. By dividing the solar spectrum this way, researchers can move far beyond the efficiency ceiling faced by a conventional single-junction silicon cell. For a 2-terminal perovskite-silicon tandem architecture, the theoretical efficiency limit can rise to approximately 43%. And this is no longer confined to tiny laboratory demonstrations. The technology is already moving toward full-scale modules. In June 2026, Chinese solar manufacturer Trina Solar introduced a commercial-scale perovskite-silicon tandem module rated at an extraordinary 907 watts, with a conversion efficiency of 29.2%. Compare that with a typical residential silicon panel producing somewhere around 400 to 500 watts. By stacking these materials together, manufacturers are attempting to extract dramatically more electricity from essentially the same roof area. For homeowners, that could completely change the economics of limited space. If your roof is small, shaded in sections, or located on a tightly packed urban property, higher efficiency tandem modules could allow you to generate far more electricity without covering additional surface area. And the records have continued to move. In July 2026, LONGi Green Energy reported another major milestone. Its independently developed crystalline silicon perovskite tandem cell reached a certified conversion efficiency of 35.5%, tested by the European Solar Test Installation, or ESTI. And LONGi was not working only with microscopic laboratory samples. The company also demonstrated efficiencies of 34.3% on a 261 square centimeter cell and 32.2% on a 274 square centimeter cell. Those larger dimensions matter because they push the technology closer to something that can eventually be produced at industrial scale. This is no longer just a small improvement to the solar panel we already know. It represents a completely different way of extracting energy from the same sunlight. Part 4. The Chinese Solar Speedrun. From Labs to Gigawatts. So why is China becoming such an important part of this story? Because Chinese researchers and manufacturers are aggressively pushing perovskite out of controlled laboratories and into the unpredictable conditions of the real world. For years, photovoltaic researchers have faced what could be called the scale-up gap. Making a tiny, highly efficient solar cell about the size of a fingernail is one challenge. Making a panel the size of a table while maintaining that same quality is something entirely different. As researchers increased the surface area of perovskite coatings, the material could crystallize unevenly. Small defects appeared. Those defects accumulated across the larger area, and efficiency dropped dramatically. Researchers at Nanjing University, including Assistant Professor Xiao Ke and Professor Hairen Tan, worked with the industrial team at Renshine Solar to attack this problem directly. Instead of relying only on conventional laboratory spin coating, they developed a lead carboxylate-based passivation strategy combined with vacuum-assisted crystallization. The treatment acted almost like a chemical repair system, reducing microscopic defects across a much larger perovskite surface. Using this approach, they produced a 0.72 square meter commercial-scale module with a certified full-area efficiency of 22.0% and a stable output of 158.4 watts. The work was published in Nature in August 2026. But the project did not stop with a laboratory module. The researchers built a 1-megawatt perovskite solar system and installed it beside a modern 3.5-megawatt silicon TOPCon system at a large ground-mounted power facility in China. That allowed the two technologies to operate under the same real-world environmental conditions. From March through May of 2026, researchers monitored their performance side by side. In March, the perovskite system generated 3.42% more electricity per unit of installed capacity than the silicon system. In April, the advantage increased to 3.79%. And by May, the perovskite system produced 5.81% more electricity than the silicon system. One major reason involved temperature behavior. Conventional silicon modules lose efficiency as their operating temperature rises. Perovskite can have a more favorable temperature coefficient, allowing its performance to hold up better as sunlight intensity and temperature increase. At the same time, China's national PV and energy storage demonstration platform in Daqing has been testing large-scale perovskite installations from companies including Utmo Light and Microquanta. Megawatt-scale systems are moving into outdoor operation, with reported performance ratios approaching 100% under real-world conditions. The speed of this scale-up is remarkable, but it also raises an obvious question. If perovskite is inexpensive, lightweight, powerful, and potentially easier to manufacture, why isn't it already covering rooftops everywhere? Because this crystal has a serious weakness. Part 5. The Achilles heel. the stability crisis. For all of its remarkable properties, perovskite has earned a reputation among researchers as something of a crystal diva. Early perovskite cells could perform brilliantly inside a laboratory. But once they encountered real-world conditions, their weaknesses became impossible to ignore. Humidity alone could cause serious damage. Water molecules could penetrate the crystal structure, interfere with the delicate bonds holding it together, and eventually cause the perovskite to break back down into its precursor materials. In some early cells, this degradation could happen within days or even hours. Researchers therefore had to confront four major environmental threats at the same time. The first was moisture. Rain, condensation, and humidity could attack the crystal structure and transform a functioning photovoltaic material into degraded lead iodide compounds. The second problem was thermal stress. Solar modules installed on rooftops can reach temperatures above 85 degrees Celsius, or around 185 degrees Celsius, during hot summer conditions. At those temperatures, volatile organic components, such as methylammonium, can become unstable and escape from the material, leaving behind a damaged film that no longer performs properly. The third problem was UV exposure and ion migration. Ironically, the sunlight perovskite cells are designed to harvest can also contribute to their degradation. Under prolonged illumination and electrical operation, halide ions such as iodine and bromine can begin moving through the crystal. That migration can trigger phase segregation, reducing the voltage and damaging performance. And the fourth challenge was mechanical fatigue. A rooftop solar panel may experience decades of heating, cooling, freezing, and expansion. Perovskite and silicon do not expand and contract at exactly the same rate. Over thousands of thermal cycles, those differences can place stress on the microscopic layers and eventually cause cracking or delamination. Traditional silicon modules have already demonstrated that they can survive hail, snow, heat, and outdoor exposure for 25 to 30 years, often with annual performance degradation below about 0.5%. Early perovskite devices could not come close to that lifetime. And that creates a simple problem. No homeowner wants to invest thousands of dollars in a rooftop energy system that might fail after a short period of exposure to rain, heat, and sunlight. This durability problem has been one of the biggest reasons perovskite has remained outside the mainstream residential solar market. But researchers did not stop there. They began rebuilding the material itself. Part 6. Rebuilding the crystal. How science solved the longevity issue. If perovskite was going to survive outside the laboratory, scientists needed to protect its fragile crystal structure from the conditions found on real roofs. One important breakthrough came from materials engineers at Georgia Tech, led by Professor Juan Pablo Correa Baena. For years, researchers often treated water and oxygen as separate causes of perovskite degradation. But by studying the material at the atomic level using high-energy X-rays, the Georgia Tech team discovered something much more complicated. Water and oxygen were working together. Neither one alone produced the same destructive effect. Instead, the most serious degradation came from a combined interaction involving both moisture and oxygen. That discovery suggested a powerful strategy. If researchers could successfully block one member of that destructive pair, they might prevent the reaction from progressing. The team applied an extremely thin layer of a water-repelling molecule called phenethylammonium iodide, or PI, to the perovskite surface. The coating behaved like a microscopic umbrella. By preventing water from interacting with the crystal, it dramatically suppressed the degradation process. But moisture was only one part of the problem. Heat remained another major challenge. Correa Baena's laboratory found that an organic charge transport material called spiro-OMTAD could begin crystallizing and degrading at temperatures around 70 degrees Celsius, or 158 degrees Fahrenheit. To strengthen this vulnerable layer, researchers turned to a method called vapor phase infiltration, or VPI. Before installing the electrodes, the cell was exposed to titanium-containing vapor under a light vacuum. This allowed tiny clusters of titanium oxide and hydroxide to form inside the organic layer. The result was a much stronger internal structure. The reinforced material could tolerate temperatures as high as 120 degrees Celsius or 248 degrees Fahrenheit without losing performance. The titanium acted almost like a microscopic scaffold, helping hold the organic layer together under heat. Meanwhile, the team at Nanjing University was seeing major stability improvements using its lead carboxylate passivation approach. During accelerated damp heat testing at 85% relative humidity and 85 degrees Celsius for 1,300 hours, conventional comparison devices lost 39% of their efficiency. The newly passivated modules lost only 2%. Even after 300 rapid temperature cycles, moving from -40 degrees Celsius to 85 degrees Celsius, the improved devices showed almost no efficiency loss. For the first time, perovskite was beginning to look less like a fragile laboratory curiosity and more like a material capable of surviving years of real-world exposure. But durability was not the final problem. There was still one major issue hanging over the entire technology: lead. Part 7. The toxic elephant in the room. The lead challenge. If hearing the word lead makes you uncomfortable, you are certainly not alone. Lead is toxic, and many of the highest-performing perovskite solar cells rely on lead-containing compounds. That immediately raises an important question. If millions of these modules are eventually installed on rooftops, what happens when one is shattered by severe hail, damaged during a fire, or broken at the end of its life? Could soluble lead compounds escape into surrounding soil, gardens, or water? This concern has become one of the biggest environmental obstacles facing perovskite technology, particularly in regions with strict chemical safety requirements, such as the European Union. But the quantity involved is important to understand. A perovskite solar module may contain approximately 0.5 to 1.5 grams of lead per square meter. That is an extremely small quantity compared with something like a conventional car battery, which contains vastly more lead. A traditional silicon solar module can also contain roughly 15 grams of lead in soldering materials. However, perovskite presents a different concern, because the lead compounds inside the active layer can be highly water-soluble. So researchers are treating containment as a critical part of the technology. One promising solution is known as on-device lead sequestration. Instead of relying only on external recycling systems, researchers are placing lead-capturing materials directly inside the solar module. One approach uses mesoporous, sulfonic acid-based cation exchange resins, or CER. These resin layers are integrated into the device itself. If the module cracks and water enters the cell, the resin reacts with dissolved lead ions through an ion exchange process. Instead of allowing those ions to escape, the resin captures and chemically binds them inside its porous structure. In aggressive, acidic water-dripping tests, the integrated resin reduced lead leakage to approximately 11.9 parts per billion, bringing it within drinking water standards. Other research teams are exploring titanium dioxide sponge layers and supramolecular complexes made with compounds such as cyclodextrin and tetracarboxylic acid. These systems can act as chemical traps capable of capturing more than 90% of leaking lead. At the same time, researchers are trying to eliminate lead completely. Scientists are experimenting with alternatives based on materials such as tin, bismuth, and titanium. Tin is one of the most promising candidates, but it comes with another serious weakness. Tin in the Cent2+ state oxidizes easily into SN4+ when exposed to air. That degradation has kept laboratory efficiencies for many tin-based devices in the range of approximately 14% to 16%. So while lead-free perovskites continue to improve, the direction for the coming decade appears much clearer. High-performance lead-based perovskites are likely to remain dominant, protected by robust encapsulation and active lead capture systems designed to prevent contamination if a module is damaged. And that leads directly to another important question. What happens when these solar cells finally reach the end of their useful lives. Part 8. Closing the loop. The ultimate circular solar economy. This is where perovskite offers another fascinating possibility. It can potentially be recycled almost completely. The first generations of conventional silicon solar modules are now beginning to reach the end of their roughly 25-year operating lives. And recycling them is not simple. Silicon panels contain glass, polymers, silicon cells, silver, wiring, and other materials bonded tightly together. Separating those layers can be expensive and complicated. As a result, enormous quantities of aging solar modules could eventually end up in landfills. Perovskite is fundamentally different. Because the active material can originally be deposited from a liquid solution, researchers discovered that it could also be removed and recovered through solution-based processes. In 2025, researchers from Linköping University in Sweden and Cornell University in the United States developed a water-based recycling method designed to recover the valuable materials inside perovskite cells. Instead of depending on aggressive organic solvents, the process used water, combined with three relatively simple additives: sodium acetate, sodium iodide, and hypophosphorus acid. The key was the interaction between acetate ions and lead. Lead iodide does not normally dissolve easily in water. But acetate can coordinate with the lead, converting it into a much more soluble lead acetate form. That allows the perovskite layer to be removed from an old device through a water-based washing process. Using this method, researchers recovered approximately 99.6% of the lead and converted it back into high-purity lead iodide crystals. They also recovered the expensive spiro-OMETAD transport material using a solvent mixture based on ethyl acetate and ethanol. The glass and transparent conductive substrates could also be reclaimed. But recovering the materials was only half of the experiment. The team then used those recovered materials to manufacture new perovskite solar cells. The recycled devices reached an average efficiency of approximately 21.9%, while the best cell achieved 23.4%. That meant they retained more than 99% of the performance achieved with devices manufactured from completely new raw materials. The life cycle analysis produced another striking result. The water-based recycling approach reduced estimated human toxicity impacts by almost 69%, compared with landfilling, and reduced the demand for virgin resources by approximately 96.6%. That is the larger promise behind perovskite. Not simply another solar panel, but a technology that could potentially become part of a much more closed-loop energy system, where valuable materials are recovered and returned to production instead of being discarded. The future of solar. Will perovskite replace silicon forever? So where does all of this leave us? Is China's rapidly advancing perovskite technology really ready to replace conventional solar panels forever? The answer is an exciting yes, but probably not in the way many people imagine. Traditional silicon panels are not going to disappear overnight. Instead, the future may be built around a fusion of the two technologies. When homeowners eventually shop for the next generation of solar modules, the decision may not be silicon or perovskite. It may simply be Perovskite-silicon tandem panels. These ultra-efficient modules combine the strengths of both materials, allowing significantly more electricity to be generated from the same amount of roof space. And rooftops may be only the beginning, because perovskite can be thin, lightweight, flexible, and even semi-transparent. It could eventually reach places where conventional rigid silicon panels are difficult to use. Imagine solar roofs integrated directly into vehicles, windows that allow daylight into a building while also generating electricity, or smart home sensors powered continuously by the ambient light already inside your home. That would represent something much larger than another efficiency record. It would change the places where solar energy can exist. This story is not only about laboratories, corporations, or massive gigawatt-scale factories. It is about a deeper change in how we might eventually power our homes and our daily lives. It is about creating homes that are more self-reliant, more resilient, and better able to use the natural energy already surrounding them. The path toward a cleaner energy future has never been perfectly straight. There are setbacks, there are fragile materials, there are durability problems, and difficult environmental questions. But what we have seen with perovskite is how quickly those obstacles can begin to fall when researchers, engineers, and manufacturers continue pushing a promising idea forward. A crystal that once survived only briefly inside a laboratory is now being tested in large outdoor installations. A technology that started below 4% efficiency is now competing with some of the most advanced solar cells ever developed. And a material once considered far too fragile for the real world is moving steadily closer to the rooftops above our heads. If this deep dive gave you a little more hope and a better understanding of where solar technology may be heading, subscribe to the channel, share this video with someone interested in home energy and optimization, and tell me in the comments, would you install perovskite-silicon tandem panels on your home today? Thank you for watching The Roots Survived. Keep exploring, keep optimizing, and I'll see you in the next one.